Now that we have a handful of EAS reactions to work from, we're going to talk about adding multiple groups to the ring. So to do that, we have to talk about activating and deactivating groups. So now instead of benzene, we're going to start looking at benzene derivatives. In this slide, you see toluene reacts with HNO3 and H2SO4. These are our reagents to put on a nitro group. But where does the nitro group go? Do we get meta, ortho, para? And how do we decide? This R group is something we call an activating group. And what we're going to learn here, activating groups are electron donating, right? So they put some extra electron density into that ring, which allows them to attack the electron more easily. Toluene reacts much faster than benzene, because it makes the ring that better nucleophile. Now, we all want to know about that regioselectivity. So let's look at the products. The ortho product makes up 63% and para 34%. Now, that can be explained, this being double that of para, because there are two positions that would give you orthonitrobenzene as compared to one position, para-nitrotoluene. But you notice hardly any meta product is made. And that's something that is, that's another note you should make about activating groups. They tend to be ortho, para, directors. They can add to the ortho or para position. Very little meta. So when I ask you for to predict a product, either one of these two would be acceptable. Those are the major products. Now, why does this happen? So I'm going to talk through one of the sigma complexes, but I will go ahead and expand that a little bit for the ortho, meta, and para attack. Once you have made the nitronium ion, so I'm going to skip the first step of that mechanism, and we are attacking the nitronium. There are 3 sigma complexes. All right, so let's review those sigma complexes one more time. You have your NO2 and an H, and then you have your plus charge. That plus charge is going to be shared by 3 of the carbons. Oh, here we go. Got to keep that NO2 in the right spot. And one last one here. It's in this sigma complex that we get our answer. That plus charge is found on the carbon with the R group. All right, so all of your sigma complexes have 3 structures, so they're all resonance stabilized. However, the meta, it goes secondary, secondary, secondary. Whereas in the ortho and para position, there is a stabilizing effect of having an electron donating group next to a positive charge, right? You can stabilize positive charge by giving it a little bit of electron density. And that's exactly what's happening here. So if this intermediate is lower in energy than the meta intermediate, then it's going to take less energy to make ortho and para. Right, and you can see that when you compare the energy diagrams. Ortho and para are both lower. Para is a little bit lower. It's usually because of sterics. Meta takes a lot more energy to make. And that is where this comes from. So when we talk about activating groups, deactivating groups, the halogens, when we talk about direction, it all comes down to the sigma complex and what was stabilizing. Not all activating groups are created equal. When we look at anisole, this activates the ring even more. Whereas toluene reacts, I think, about 25 times faster than benzene, anisole reacts 400 times faster. Now, it may be counterintuitive at first because you think, oh, oxygen is more electronegative. But there's also lone pairs on the oxygen, so you can draw resonance structures where those are being donated into the ring. And you can see an actual negative charge, here in the ring. And so that is reflected, of course, in that increased rate. This is also an ortho-para director. Of course, it's activating. All that we're saying here is that it reacts so much more quickly that poly substitutions are very likely. I'm not going to ask you to focus on that. Again, you only make a very small amount of that meta product. However, you kind of see a switch between ortho and para. There's still two ortho positions, so why is there more para? The OCH3 is bigger than the CH3, so it's just a little bit harder to get into the ortho position than to get to the para. It's still perfectly acceptable to call both of these the major products. When you compare the resonance structures, you actually see that ortho and para is even more attractive because not only does that plus charge wind up next to the electron donating group, you get a fourth resonance structure. So anytime the, the substituent has a lone pair, all right, so this is the ortho-para directing substituent, has a lone pair, you get a fourth resonance structure, a fourth structure in the sigma complex. Anytime you have resonance, right, that's stabilizing, the more resonance structures you have, the more stabilizing it is. So, there we go. We don't just benefit from the additional substitution on the plus charge, but from actually being able to spread that plus charge out onto an additional atom. And that only works in the ortho and the para case. In the meta position, you still just have 3. So you can see ortho and para, again, fairly low. The difference is a little bit more because of the steric hindrance. The meta position, it takes too much energy to work. Now, you have some information about activating groups, electron donating, and their OP directors. They're OP directors because of the sigma complex. Either you wind up with a more substituted sigma structure, or you wind up with something like anisole, you wind up with a fourth resonance structure. So let's take a break from that for a moment, and let's focus on deactivating groups. Anything that's pulling electron density away is going to fall in this category that's pulling electron density away inductively and through resonance. Something like a nitro group is deactivating. They also slow the reactions down. So while you still could make, now you can't do Friedel-Crafts, but you could still put a bromine on. This is going to be slower than if you just had benzene by itself. Now, things about most deactivating groups. are meta directors. Most. Of course, I'm going to give you an exception in a minute, so write the word most. It prefers that meta position. 93% meta, very little para, very little ortho. Why? Why does this occur? Let's look at the sigma complex again. In the ortho and the para position, now what's highlighted in green is not favorable. Putting that plus charge directly on that nitro, or on the carbon with the nitro group, is going to be high energy because you already have a strong pull of electrons away. So if you have an electron deficient carbon, that's going to create more stress. However, with meta, that plus charge avoids being on the carbon with the nitro group. So it's not really that meta forms faster, or, I mean, it does. It's not that meta is just so much better. It's that ortho and para are so much worse. And you can see that in the energy diagram. They're all fairly high. Meta is just less bad, right? So meta is just less deactivated. It's still going to go slow, but it will go to the meta position. Now, the reason I said most, the halogens are the little weirdos. They are deactivating, so they do slow down the reaction. But they're also ortho-para directing. What? How is this possible? Well, they are electronegative, so they pull electron density away from the ring through the sigma bond. However, they also have lone pairs that can donate to the ring through resonance. So we wind up getting a slower reaction, but one that favors the ortho and para position because of that additional resonance structure. Remember I said any substituent with a lone pair is going to direct ortho para and give you a fourth resonance structure. The meta position has the plus charge avoiding the C with the chlorine, so it cannot share that positive charge with a fourth atom. So again, we have a more stable intermediate. That is where the direction is going to go. If we have chlorobenzene, the nitro is going to go to the ortho or the para position. Now, these slides are going to list out exactly the chart that I'm going to make over here. I just like the way I write it better. And I think you should write it this way as well for while you are practicing over the next few days. We are going to go from strong activator to moderate to weak. All right, so everything above this blue line is an activator. I'm going to put A's here. Then we're going to go from weak deactivator to moderate to strong deactivator. All right, so activator. So if we have something in this list, right, benzene rings with substituents at the top, those reactions are going to go the fastest. At the bottom, they're going to go the slowest. Now, what constitutes a strong activator? So you should assume these are all attached to benzene rings. But alcohols, anything with a negative charge on it, because that can definitely donate electron density, and anything with nitrogen. It could be primary, secondary, or tertiary amine. These are all strong activators. The moderate activators, I'm going to throw OR in here, and then I'm going to make two more. Anything that is an O carbonyl or an N carbonyl also would be moderate. These still have lone pairs directly attached to the ring, so they would give you a fourth resonance structure. And then, before we move on, it doesn't really matter what's on the other side. It doesn't matter if it's an H or an R or an OH or it's ring, oxygen, carbonyl. There's only one group in the weak activators. That's just your alkane pieces. These are weak. They give you ortho and para because of the more stable tertiary carbocation that you get, but they don't have a fourth resonance structure. Weak deactivators, and see they go in a different order here. Weak deactivators are your halogens. So what I like to do is then change my color here, and I put a red line. All right, blue line above is activators, below is deactivators. Red line above is OP directors, below is meta directors. Moderate deactivators, this is pretty much going to be anything with the carbonyl directly attached to the ring. It could be ketone, aldehyde, ester, carboxylic acid, or amide. Also your sulfonyl group, so the SO3H, that's a deactivator, that's a meta director, and nitriles. The strong deactivators, the one that I really want you to know is NO2. It's not bad to know the quaternary positively charged nitrogen. It doesn't have to just be oxygens attached. I'm not going to ask you about this one, but if you replaced all the hydrogens on a methyl with like fluorine or chlorine, that would actually change it from a moderate activator to a strong deactivator. But I'm going to focus on these two. Now, this is really important to know this list because if you have to add to a ring that already has two groups, then you've got to be able to decide which one of those is more important. And how am I going to direct? To ortho, to the methyl, meta to the nitro? Sometimes they agree, sometimes they don't. You need to be able to do a tiebreaker. So we're going to do some practice problems with this. Now, we're going to start off just looking at this example here. This is an example where the two substituents direct to the same carbon. Your CH3 directs to ortho-para. Well, the para is blocked. You're only going to substitute for a hydrogen. You're not going to replace anything else. The nitro group directs to the meta position to the nitro group. So both substituents are directing to the same places. So bromine is going to go ortho to the methyl. It could also have been on this side. It will not go here. It will not replace the NO2. But sometimes they disagree. The OH is an ortho-para, and the toluene is an ortho-para. So which way does it go? Whichever is higher on the list that we have off to the right here, that is the one that wins. That's the one that takes priority. So I don't like to say the stronger because, a weak deactivator would take priority over a strong deactivator. It's whatever is higher on this list. So since OH is a strong activator, CH3 is a weak activator, nitro is directed by the OH. Okay, let's do one more thing. So let's do a couple of practice problems. So if we only have one substituent and we are, let's do HNO, oh, I've made a mistake, HNO3, H2SO4. Let's say we are nitrating. Well, I only have one substituent, so I need to know where on the list it is. SO3H, it's a moderate deactivator. So it's going to be a meta director. I can put my nitro group here. I could also put it here. It gives this the same product, so you put it on whichever one you want. What about if we have something like here we go. We have a chlorine, which is a weak deactivator, but it's an ortho-para director, which is important. So that could have been here or here. And we have a carbonyl-containing compound. That's a meta director. So it is, I gave us an example of directing to the same place. Now, I would take either answer as the correct answer. If I ask you for a major product, I might put let's say we were doing a bromination, Br2 and FeBr3. Well, that would put my bromine probably in the para position here. You could also put it here. There's just going to be less steric hindrance. Not that chlorine's very big. Either one would be fine. If we had, let's say we had 3 substituents. Let's say we have an 08. Let's mix it up a little bit. Let's say we have an amine. We have a ethyl. And we have a nitro group. Say now we're trying to add a sulfonyl. We want fuming H2SO4. The same rule applies, right? The amine is directing, because it's a strong activator, to the ortho positions. If I want to look at the ethyl group, it is directing ortho and para. And the nitro group is directing meta. Oh my gosh, how did I do that? They're all directing to the same place. If I had to make a choice, though, the ammonia would be the one that would be a tiebreaker. Now, if I have to choose a position, I'm going to go for this side, because going between the ethyl and the amine, it's going to have more steric hindrance. So I'm going to choose to put my sulfonyl group over here. There's less steric hindrance. There's practice in your old homework assignment on eCampus. Definitely be practicing with this, because in the next video, we are going to talk about multi-step synthesis.